Wolf Rayet stars are so powerful, they literally tear themselves apart. They also create the very elements that make life possible. Up to a quarter of the oxygen we breathe and carbon in our bodies come from these very stars. But how do these destructive forces create the very components for life? And why do they tear themselves apart? In 1867, two astronomers, Charles Wolf and George Rayet, observed 3 stars. To see what the stars were made out of, they attached a prism spectroscope to their telescope to break the starlight into individual lines. But instead of seeing their sharp absorption lines like an ordinary one, they found broad emission lines on all 3 of them. This clearly suggested that what they saw was out of the ordinary, something unusually hot and bright. However, it was also the first observation of what we now call Wolf Rayet stars. So why are they blurring the emission spectrum? At the time, astrophysics was still a newly developing field. Spectroscopy had just begun to show that stars were mainly made out of hydrogen like our sun, and there were no leading theories until half a century later. In the early 1900s, astronomers initially thought that these emissions might be from the surrounding luminous gas shells instead of the star itself. However, this theory quickly fell apart after calculating the velocity of the gas, deduced from how broad the lines are by using the Doppler effect. How did they do it? You've probably heard of the Doppler effect, like when an ambulance siren changes pitch as it speeds past you. A similar effect happens with light, although instead of the pitch of the sound, it's the color of light. When an object moves towards us, its light is blue shifted. When it moves away, its light is red shifted. This then makes the emission and absorption line shift on the spectrum as well, and the gas near Wolf Rayet stars move in all sorts of directions, causing the effect of redshift and blue shift to happen simultaneously. This causes the lines to broaden on the spectrum as a result. One side appears blue shifted, while the other is red shifted. By measuring how blurred the emission lines are, we can determine the velocity of the gas shell. However, one problem is that the gases must reach speeds of 2,000 to 3,000 kilometers per second, much faster than any known nebula motion at the time. Plus, if it originated from the star, it seemed absurd, at least during that time, that there is a mysterious force, somehow stronger than gravity on stars. So how were the gas shells expanding that fast? Wolf Rayet stars are often found in a binary system, so 2 reasonable explanations would be that 1. The expanding gas shell was caused by a previous event such as a supernovae from its companion star rather than the Wolf Rayet star itself. Or 2. A cooler explanation is mass transfer. Gravity creates zones called Roche lobes, which define where each star's gravitational pull dominates. If one star expands or sheds gas out of its lobe, some of that material can spill out and be pulled towards its companion. Some of these mass can either be exchanged to the other star or be accelerated into outer space at high velocities, a bit like gravity assist. But unfortunately, lone Wolf Rayet stars show the same broad emissions, meaning that it can't be from the interaction with its companion star. Many other theories were also disproven many times. The real breakthrough would not emerge until the mid-20th century. They officially confirmed that these fast-moving gases were indeed coming from the star itself and ejected outwards, but had no idea what mechanism could make this happen. During that era, James Clerk Maxwell demonstrated that light carries a momentum, proving that light can push matter, named radiation pressure. So yes, light can actually push things. No, you can't fly by shining a flashlight at your feet. To be more specific, atoms actually prefer to absorb light that matches their absorption lines. Photons aligning with the absorption lines have a high probability of exerting a force on the atom, while unaligned light is very likely to be scattered or pass through the atom. Take hydrogen for example. Light matching these lines are much more likely to be absorbed and therefore transfer their momentum to hydrogen atoms. And wavelengths that don't match will be scattered or passed through, so hydrogen is affected more by these colors than the rest of the spectrum. Using Maxwell's idea of radiation pressure, Arthur Eddington proposed that the radiation from the star could push matter outward in addition to the internal gas pressure that keeps stars from collapsing under their own gravity. Many historical scientists expanded on this idea, suggesting that especially for hot luminous stars, radiation pressure could cause continuous mass outflows. And what are Wolf Rayet stars? They are extremely hot and extremely luminous. So decades later, in the 1970s, Castor, Abbott, and Klein proposed a potential explanation to the high-speed winds called the CAC theory. What they discovered was remarkable. Simultaneously, researchers observed a particular type of stars and realized that Wolf Rayet stars are not anomalies separate from the stellar life cycle, but actually a brief phase in the life of O-type stars. These stars often have a mass of 25 to 30 times the mass of the Sun. And like Wolf Rayets, they generate immense luminosity and powerful stellar winds. A few decades ago, they also saw that over time, some may go through a luminous blue variable phase, or LBV phase. These phases are unpredictable events of outbursts that tear their outer layers into space significantly. Likewise, Wolf Rayet stars are very luminous. Their hydrogen layers are light enough to be ripped off entirely into space via radiation pressure alone, exposing the inner layers into the rest of space. So it's clear that there's a connection between the two. With hydrogen mostly gone, elements like helium, carbon, oxygen, and iron overtake the surface. Interestingly, iron has numerous absorption lines. This means that it grabs more light, being a lot more affected by radiative push. This is why O-type and WR stars experience a radiative push magnitude stronger than a Sun-like star just from its metallic composition. The astrophysical term for this is metallicity, which is how much metal a star has compared to the amount of hydrogen and helium that makes it up. Yet as promising as the CAC theory was for O-type stars, its predictions fell short when applied to extreme conditions of Wolf Rayet stars. Their winds were far more ferocious than the model could explain, hinting at a hidden detail we were missing. For years, scientists needed a better theory for Wolf Rayet. Their winds were more extreme, and the theory couldn't account for the massive amounts of mass being expelled. It wasn't until late-night sessions with spectral data that the breakthrough happened. Researchers noticed that the absorption lines weren't static. They were shifting due to changes in velocity from the outflowing gas. These shifts weren't random. They revealed that different layers of the stellar wind were moving at different speeds, hinting at an accelerating mechanism beyond simple radiation pressure. This realization led to a breakthrough. After years of refining the CAC models and debating possibilities, they realized that the answer was hidden in the motions of the winds themselves. Let's say you're a helium atom, sitting in the outer layers of a Wolf Rayet star. As a helium atom, you mostly absorb wavelengths of light that match your absorption lines and gain momentum. However, since the star emits so much light, the group of atoms you're in becomes too saturated, meaning this region of gas cannot accept any more photons, even if they align with the absorption line. This is because they already ate their maximum amount of energy. Photons are essentially blocked or shadowed by the atoms that are already absorbing the light. Now, you and your neighboring atoms are all accelerating outwards from the star. Although not all parts move at the same speed, there is a gradient, meaning different layers of gas have slightly different velocities. Because of this, the Doppler effect becomes important. Each layer in a region will see light shifted by a different amount than another, allowing photons at a slightly different frequency to be absorbed in regions that aren't yet saturated. In essence, if you were to average the absorption across this region, you would get a broadened absorption line, each layer absorbing light at a slightly shifted wavelength. This de-shadowing means that more photons can interact with the gases and as a result, gain more momentum, causing a continuous acceleration until the gas escapes from the star. Feel free to rewind, it can be a lot to take in. So because hydrogen is absent in Wolf Rayet stars, and instead has efficient light-absorbing elements, it makes the star more affected by radiation pressure. Moreover, They can be up to 1,000,000 times more luminous than our sun, making radiation pressure magnitudes stronger. And like how hot water turns into steam, the extreme heat gives atoms enough kinetic energy to escape the star. At last, the Doppler effect creates a positive feedback loop that further accelerates winds into space. Because of how rapid Wolf Rayets lose their mass through stellar winds, there's of course a consequence. Our sun loses around 3 moons worth of mass per year from stellar winds alone. Wolf Rayets, on the other hand, can lose that in minutes, 1 Earth worth of mass every single day. From this rapid shedding, these ultra-bright stars have very short lifespans, only a few million years, roughly 10,000 times shorter than the sun's. But how do these stars even exist in the first place? The answer lies in their life cycle. Early studies compared Wolf Rayet stars with O-type stars, noting that both eject mass, though in very different ways. Over time, O-types lose their outer hydrogen layers from LBV phases and winds, making the deeper and hotter layers become exposed. These previously hidden layers are full of helium and other heavier elements like carbon, nitrogen, and oxygen. This officially marks the Wolf Rayet phase. There are no longer hydrogen layers to weigh down the intense radiation pressure that will go against the more light-absorbing particles. And as we know from before, the particles will zoom off into space at a fraction of the speed of light. So, how do these give us the very elements for life? Supernovae. As O-types transition into Wolf Rayet stars, nuclear fusion progresses. Heavier elements such as carbon, oxygen, and silicon are formed until the iron core develops. Since iron fusion does not produce energy nor internal pressure, the core can no longer support itself against gravity. It collapses into itself and triggers a massive supernova. These typically appear as type 1b or 1c, which are both characterized by the lack of hydrogen and in some cases helium in their spectra. And what happens to the core? If the collapsing core manages to gather enough mass, it may form a black hole. Otherwise, it becomes a neutron star. Meanwhile, the material ejected during the supernova spreads out at great speeds into the surrounding interstellar medium with heavy elements such as carbon, oxygen, and neon. These chemical elements are essential to the formation of future stars, planets, and even life. A good portion of what made us, Earthlings, come from these very stars. Over the course of history, us humans have seen that Wolf Rayet stars are extraordinary. They are massive stars with their outer hydrogen layers ripped off into space. They release extreme radiative winds that diminishes our sun in perspective. Their turbulent lives, shown by the rapid mass loss and explosive deaths, not only light up the sky with vibrant supernovae, but also pepper galaxies with heavy elements crucial for life. In short, these stars are both stellar destroyers and creators. The heaps of scientific findings and centuries took to understand these mysterious dots in our night sky. Recent research on Wolf Rayet stars has led to significant advancements in our understanding of their evolutionary pathways, their role in binary systems, and their contribution to supernovae and gravitational wave events. In a way, you owe a part of your existence to these brief but powerful stars. The more we understand them, the more we can see how connected we are to the stars. From the biggest explosions in space to the atoms in our bodies. And with every new discovery, we get a little closer to understanding how the universe built itself, and in turn, how we got here in the first place. But here's the kicker. One day, you will die. Your body will be decomposed and your atoms scattered slowly but inevitably. Some of you will evaporate into space and eventually become a part of another star. Maybe a planet, maybe even another life form that looks up at the night sky and wonders, where did I come from?